So, we're going to go through a scale of the planet Earth. And I've got this up on the screen, but I've got this tape measure running around the floor. It turns out that it's 45 feet from that wall to this wall, and from here to the edge of the doorway. Let's make every foot of this 45 feet equal to 100 million years. And I'm going to pace out the history of the planet on that 45 feet. Well, before the planet existed, of course, there was a cloud in the universe, and gravity pulled it all together. And about here, enough of that hydrogen, which was, of course, this cloud is mostly hydrogen, had condensed into a ball that reached ignition temperature, ignition for nuclear fusion. And the sun lit up. Around this sun were streaks of gas and heavier elements, primarily silica and iron and so forth, that began to coalesce around orbits around this sun. And about here, 4.5 billion years ago, the Earth reached about its modern size. That is, it had all coalesced, and a catastrophe happened. This nascent Earth was struck by a small planetoid and ejected a large chunk of the crust, which recoalesced and formed the moon. There are a lot of details of this that are unclear even yet. This was not, essentially, we have a binary planet, right? The Earth and the Moon are close enough in size that we really, if we saw somewhere else, we would call it a binary planet, as we do Pluto and Charon. Earth, however, continued to be bombarded by large chunks of stuff that were still coalescing in the early universe. And so, for the next 300 million years, these chunks would strike the planet, and with such force that the crust would be completely melted. Probably much of it vaporized, blown out into space, and then it would recollect on the planet. The atmosphere would have been stripped from the planet, the liquid ocean on the surface would have been completely vaporized, and then had to recondense. In between times, in the absence of a greenhouse effect, the planet would have frozen solid on the surface. And so we went back and forth through several phases of completely frozen desert planets to planets with molten rock crust and little or no atmosphere, maybe steam. We would consider these sterilizing impacts, right? If any origin of life happened in the interim, these impacts would have been sufficiently energetic to have eradicated that life, and life would have had to start again. At about 3.8 billion years, however, the last of these bombardments occurred, and Earth was more or less the size that it is now, within the margin of error, and the last of these sterilizing impacts was in the past. The oldest rocks we have date from this time, and so any rocks that existed before that have been transformed so completely that they're not really the same rocks anymore. There are a few places on Earth where rocks from this time period still exist and are available to us. Western Australia, Greenland, a couple of other places. Not very many. $3.6 billion years ago, unequivocal evidence for life on Earth. And so life originated sometime in the last 200 million years and populated the planet. The evidence for this are fossilized stromatolites. These are microbial mats in shallow marine seas. Isotope effects of the sort that we're going to talk about for the paper today. That is clear evidence for carbon fixation enzymatically in these carbonaceous fossils. Let's see. 3.4 billion years ago, photosynthesis was invented. And so prior to this, apparently, energetic production or harvesting by microbes would have been through oxidation reduction reactions only. But at this point, photosystems of some kind were invented, and what I mean by photosynthesis primarily is the isotope evidence we have for this is a carbon fractionation that represents rubisco. 3.2 billion years ago, the paper we're talking about today happened. So this is the time scale that we're looking at. 30 feet, where is this? 59, 30. At this point, the crust of the Earth fractures and the tectonic plates form. And so prior to this, the tectonic plates the crust was thin enough that it could adjust in size and so forth, and it didn't need to form solid plates. But at this point, the tectonic plates, more or less as we know them today, formed. And this means that the first continents would have formed at this point. Prior to this, there would have been shallow seas of various kinds. Sedimentary rock would have formed, but there would have been no crust that stuck above the surface of the ocean to speak of. And so continents formed at this point. 2.7 billion years ago, traces of oxygen appear in the atmosphere. So oxygenic photosynthesis is clearly happening at this point. And these organisms producing oxygen by oxygenic photosynthesis are dumping this waste product into the atmosphere. Oxygen is pretty corrosive, right? But before this, the oceans are rich in reduced iron, ferrous iron. And as the oxygen goes into the atmosphere, it's sucked up by the ocean water to oxidize that iron, and the ferric iron, which is insoluble, sinks to the bottom and forms sedimentary rocks. It forms bands of iron precipitate. These are called the banded iron formations, and they're used because these iron formations, the polarity of the crystals follows the Earth's magnetic field. There's this great history during this period of various reversals of the electromagnetic poles of the planet Earth, and provide great evidence for the spreading of tectonic plates, because these things form as new plate is emerged, and you can follow the history of the plates with these banded iron formations. 2.4 billion years ago, catastrophe strikes. All that iron in the ocean is used up, and now this oxygen begins to accumulate in the atmosphere. The Earth until this point has been essentially anaerobic, and the greenhouse effect is maintained by atmospheric methane generated by methanogens, methanogenic archaea, which are strictly anaerobic. Oxygen begins to accumulate, the atmosphere becomes less reducing, methanogens largely die off in many parts of the world, and the oxygen in the atmosphere just begins to accumulate and accumulate. The greenhouse effect goes away because methane concentrations in the atmosphere drop, and you get a snowball Earth. And so the surface of the entire ocean freezes. Is there any place like that in the universe today? I see a yes. Europa. What's the other one? Titan, I think it is. These are moons of Saturn and Jupiter with liquid surfaces covered in ice. And this is why NASA is so interested in these planetoids right now. Because if there is life in our universe, that's anything that in any way resembles what we know it now, it might be there. And so probes are being planned to send to these planets. I heard a great experiment that NASA had planned for Europa. The problem is it's a wade through that ice to the liquid part of the ocean. These liquid oceans are water, rich in ammonia. Often it's very saturated with brines of various kinds. How do you get down there? Well, their plan was to send these enormous 2-ton dicone projectiles, which you can wind up to enormous velocities through gravitational slinging, that would impact the planet right on the edge of the surface of the planet as you would view it from the Earth at a time when there was a star behind them. The notion being that if you can eject a great big rocket of steam from the impact, you can take a spectrum of that steam and look for stuff like photosystems, look for chlorophyll, look for opsins, look for FAD. Great experiment. The folks at NASA were reluctant to look for life on other planets by shooting a giant gun at it, all right? And so that experiment has been next. All right, where are we? So the concentration of oxygen in the Earth's atmosphere goes to about 5% of its current level. So what is that? That's 3 or 4% oxygen instead of 20% that we have today. Don't know much about what happens for a while here. 10, 11, 1.2 billion years ago, the first colonial animals emerge. And so at this point, eukaryotes, bacteria, archaea have colonized the whole world. And the first multicellular animals, very primitive sponge-like things, appear in the fossil record. Let's see, 8 feet 5 inches. 8 feet 5 inches. Another snowball Earth. Oxygen concentrations go up, methane and CO2 in the upper atmosphere go down, the greenhouse effect largely fails, and the surface of the planet freezes. In fact, this happens twice in the next little bit, in the next 200 million years. And so it happens here at 8.5 or 0.85 billion years and at about 0.65 billion years. Oxygen concentrations have increased significantly at this point. They are approaching about 10%, 20% of modern levels. And at 635 million years ago, the Cambrian Explosion occurs. How many of you know what I mean by the Cambrian Explosion? Very good. All of the modern phyla of animals emerge essentially within a few million years, an enormous diversification of animal life. Excuse me, 5.4. And the concentration of oxygen in the atmosphere jumps to its essentially modern level. And those two things are simultaneously enough that that's probably not a coincidence. That large multicellular animals require oxygen concentrations high enough to support them. And so, here we are, 85% of the way through Earth history, and all of life on planet Earth has been microbial, and our atmosphere has been unable to support your life. And so when people complain about going to some planetoid or something, and oh yeah, we might be looking for life there, but if there is, it's only microbial and it's a poisonous atmosphere. That's okay, because that's Earth for most of its history. 465 million years ago, 4 feet 8 inches away from the wall, plants begin to colonize the continents. 450 million years ago, there's another snowball Earth. The Ordovician mass extinction occurs. Something like 85% of species are lost. The cause for this is a little unclear. Probably massive volcanism. There are some volcanic deposits in northern Russia that may represent this volcanic event that would have injected huge amounts of sulfur into the upper atmosphere and caused an overload of the greenhouse effect, resulting in this snowball Earth. 3 feet 7 inches. The first trees appears. These trees, of course, were fossilized, the carbon compressed underground, and these are the coal deposits and oil deposits that we burn in our cars and our fireplaces today. The first insects appear, and amphibians invade the land surface. So when you've seen the picture, you know, of the fish with kind of arm-like things and a baseball bat, and there's a ball up on the coast, and they're all looking at each other like, who's going to climb up on that land? That happens right here. 3 feet 2 inches. Reptiles are invented and they begin to dominate the land surface. 3 feet itself. The supercontinent Pangaea forms. And so at this point, we don't really have a good idea for what the continents look like. But at this point, all those continental plates come together and you end up with a single large supercontinent covering, that makes up the large majority of land surface on the planet. 2 feet 6 inches. There we go. The Permian Extinction occurs. Again, what exactly causes this is unclear, probably some climatic event. 96% of species go extinct. On this day, multicellular creatures came this close to extinction. These are both land and marine creatures. The Age of Reptiles, as people generally call it, occurs, and in the beginning of the Mesozoic era that you probably all heard about begins at this point. 2 feet 2 inches. Dinosaurs and mammals emerge in the phylogenetic history. So mammals and dinosaurs originated about the same time. 2 feet, the Triassic Extinction occurs. And so this is another one of these. It may have been an impact, may have been volcanism, that's entirely unclear. But at this point, a large number of the large reptiles on land went extinct, and as a result, the dinosaurs began to take over. And so they filled these ecological niches previously held by larger non-dinosaur reptiles. And so at this point, the age of the dinosaurs, as you normally think about it, starts. 1 foot 9 inches, the fragments of this large supercontinent begin to spread out to form the continents kind of the way we see them today. 1 foot 7 inches, a particular group of dinosaurs which have feathers figure out how to fly, if dinosaurs can figure anything out at all. We call those animals birds today, and are the only remaining cloud of dinosaurs that survived the extinction I'm going to talk about in a minute. 1 foot 4 inches, 130 million years ago, flowers were invented. And so at this point, all plants were non-flowering plants. 65 million years ago, 6 inches from the wall, Earth is hit by an asteroid. It hits in the Gulf of Mexico, and the dinosaurs are extinguished. Much of life on land is extinguished. Probably not by directly by the impact and the shock wave and so forth that would have caused, but by climatic effects that occurred after that, what people would call a nuclear winter. One inch, the first hominids appeared. Not Homo sapiens, but the first human-like creatures. 1/2 millimeter, I'll call it the thickness of this paint. Homo sapiens appears, so our species, about 200,000 years ago. 10 microns, certainly the biofilm on this is thicker than 10 microns, probably much thicker. Agriculture is invented, and the first things that we would call human civilizations emerge. 1/2 nanometer. I can't do 1/2 nanometer with my fingers, all right? The U.S. declares independence from England, and 500 angstroms ago, you're born. So this is the time scale we're talking about. All the events that took place in this period, those kind of events happened all along here, right? We just don't know about it. Wouldn't it be cool if we could? The problem is that those traces are largely erased. All right, so let's talk about one time span in there.